what is an areneous acid? Areneous acid. Areneous acid is species which gives out a proton. They are termed as areneous acid. Species which gives out a proton. Proton means H plus ion. They are termed as areneous acid. Example is HCl. HCl can dissociate to give us H plus ion and Cl negative ion. So because of this H plus ion which it dissociates out, gives out, it is called as areneous acid. Now what is areneous base? Areneous base. Areneous base is species which gives out hydroxyl ion. So what is hydroxyl ion? OH negative ion. For example, NaOH. NaOH can dissociate to give us sodium ion and OH negative ion. So because of this OH negative ion, this species is called as areneous base. So Arrhenius base could not explain why ammonia is a base. So another scientist came, which were Bronsted and Lowry. So Bronsted and Lowry changed the definition of Arrhenius base, and they said that any species which accepts a proton, they will be called as Bronsted-Lowry base. So species which accepts a proton means H plus ion, they are termed as Bronsted-Lowry base. Example, ammonia, NH3. NH3 can accept a proton and form ammonium ion. This is called ammonium ion. Now, what is Bronsted-Lowry acid? Bronsted-Lowry acid remains the same as the Arrhenius acid. Bronsted-Lowry acid. So species which gives out a proton, they will be termed as Bronsted-Lowry acid. Species which gives out a proton, they are termed as Bronsted-Lowry acid. Example, we can take some other example like H2SO4. H2SO4 can dissociate to give H plus ion and HSO4 negative ion. So because of this H plus ion, it is called as Bronsted-Lowry acid. Okay, so what is an alkali? What is an alkali? Alkali are the soluble bases of group 1 and group 2 metals. So soluble bases of group 1 and group 2 metals are called as alkalis. For example, sodium hydroxide, potassium hydroxide, calcium hydroxide, magnesium hydroxide, and so on. So what is group 1 and group 2? Group 1 and group 2, they are alkali and alkaline earth metals. So if you see the periodic table, you will find group 1 and group 2. So in group 1 we have lithium, sodium, potassium, rubidium, cesium, francesium. In group 2 we have beryllium, magnesium, calcium, barium, radium. So there is a very important point. All alkalis are bases, but all bases may not be alkali. All alkali are bases, but all bases may not be alkali. Why? Why? Because we see that ammonia is a base. Ammonia is a base. Which base is it? It's a Bronsted-Lowry base because it can accept a proton. But it is not an alkali. Why? Because it is not a soluble base of group 1 or group 2 metals, but not an alkali. So all alkalis are bases, but all bases may not be alkali. Okay, now next is amphiprotic. What are amphiprotic species? Amphiprotic, so those species which can act as Bronsted-Lowry acid as well as Bronsted-Lowry base, they are termed as amphiprotic species. Species which can act as both Bronsted-Lowry acid as well as Bronsted-Lowry base. Okay, as well as Bronsted-Lowry base, they are termed as amphiprotic species. For example, water. Water is amphiprotic. Why? Because water can dissociate to give H plus ion, and because it gives out H plus ion, it behaves as an acid. Water also acts as a base, Bronsted-Lowry base, because it can accept a proton and form hydronium ion. This is called hydronium ion. So water is an amphiprotic species. It can act as Bronsted-Lowry acid as well as Bronsted-Lowry base. Another example of amphiprotic is zwitterion. So what is zwitterion? This is CHrCO negative and NH3. So we see this ion has positive charge as well as negative charge. This ion is called zwitterion. So this ion can accept a proton and can form this species CHR and COOH. Now this species can lose a proton and again we can get zwitterion. Now this zwitterion can lose a proton from this NH3 plus and it can form NH2 CHR COO negative. Now this species can accept a proton and we can again get the zwitterion. So zwitterion can accept a proton, it can lose a proton. So this is amphiprotic species. Now what are amphoteric species? Amphoteric, so the species which acts as both acid and base, they are termed as amphoteric species. Species which act as both acid and base. They are termed as amphoteric species. Example, we can take example zinc oxide. So zinc oxide can act both as acid as well as base. Al2O3, aluminium oxide, and all other amphiprotic species such as water, zwitter ion, they are all amphoteric. So the very important point is that all amphiprotic species are amphoteric, but all amphoteric species may not be amphiprotic. All amphiprotic species are amphoteric, but all amphoteric species may not be amphiprotic. For example, zinc oxide, right? Zinc oxide. So zinc oxide is amphoteric, but not amphiprotic. Why? Because zinc oxide don't have a proton to lose, and also it don't accept a proton. So this is not amphiprotic. It is not Bronsted-Lowry acid or base, but it can act as general acid or base. Therefore, it is amphoteric, but this is not amphiprotic. Okay, so now we are going to study what are conjugate acid-base pair. Conjugate acid-base pair. Conjugate acid-base pair. So what are conjugate acid-base pair? Pair of species which differ by only one proton. What is proton? Proton is H plus. So pair of species which differ by only one proton, they are termed as conjugate acid-base pair. For example, we have HCl dissociate to give H plus and Cl negative. So this is an acid and its conjugate is a base. So this is a base. So HCl is an acid and this is its conjugate base. You see this Cl negative differ from HCl by only one proton. So our pair is HCl and Cl negative. This is our conjugate acid base pair. Another example, H2SO4 dissociate to give H plus and HSO4 negative. So we see that HSO4 negative and H2SO4, they are our conjugate acid base pair. So this is our acid and HSO4 negative is our base. So very important thing, strong acid will give us weak conjugate base and weak acid will give us a strong conjugate base. So strong will give us weak, weak will give us strong, acid will give us base, base will give us acid. So here our pair is H2SO4 and HSO4 negative. Okay, now this HSO4 negative can again dissociate to give us H plus ion and SO4 2 negative ion. So now here our HSO4 negative and SO4 2 negative, they are pairs, conjugate acid base pair. So this is now acting as an acid because it is donating a proton, giving out a proton, and SO4 2 negative acts as a base. So our pair are HSO4 negative and SO4 2 negative. Okay, tell me one thing. Can H2SO4 and SO4 2 negative acts as a conjugate acid base pair? No, they don't act as a conjugate acid base pair. Why? H2SO4 and HSO4 negative, do they act as a conjugate acid base pair? No. Why? Because they differ by 2 proton. They differ by 2 proton, and the basic definition of conjugate acid base pair tells us that conjugate acid base pair are the pair of species which differ by only 1 proton.